Hi, I am Parker Kai, and today we are breaking down the attention layer in Transformers. What's really happening under the hood, why it changed the game so quickly, and how it expanded from language into computer vision. This comes right after deep networks and CNN architectures. So I will assume you are familiar with how neural networks learn features through layers. What we are focusing on here is the attention mechanism that make many of those early architectures feel almost outdated overnight. Before transformers, if you wanted a neural network to handle sequences, you use recurrent neural networks. RNNs process one token at a time, feeding each step's output into the next. It has two big problems. First, you cannot do parallelization. Every step waits on the step before it. Secondly, there's this vanishing gradient problem over long sequences. So by the time the network looks back at the beginning of the sentence, the signal is almost gone. It just simply forgets what it learned at the beginning. In 2014, Suscover showed you could do machine translation with two RMMs, one to read the input and one to write the output. This was called seek-to-seek. It worked surprisingly well, but there's a catch. The entire input sentence had to squeeze through a single fixed-size vector. Short sentences came through fine, but longer ones lost meaning because that one vector couldn't hold everything. In the same year, Badano came up with a fix. Instead of forcing the decoder to work from just one summary vector, we could let it look back at every position in the encoder and decide what's relevant at each step. That look back and choosing what matters was attention, but it was still running on top of slow sequential RNNs. Fast forward to 2017. Vasmani and colleagues at Google asked the obvious next question. What if we could get rid of the RNNs entirely and just use attention? That paper, Attention is All You Need, gave us the transformer. It is fast to train, fully parallelizable, and more accurate. GPT, Claude, Gemini, and every state-of-the-art model we use today comes from this paper. Here's what changed architecturally. On the left is the seek-to-seek model. An encoder reads the input, compresses it to a state vector, and a decoder generates the output. On the right is the transformer, the same encoder-decoder structure. But the recurrent blocks are replaced with multi-head attention, stacked n times. Let's zoom into this attention block and see how it works. So how does self-attention actually work? It comes down to three things: query, keys, and values. Each input vector gets multiplied by three separate learn matrices to produce a query, a key, and a value. The query asks, what am I looking for? The key says, what do I contain? And the value carries the actual information that gets passed forward. On the right, you can see the flow from the original paper. Queries and keys go into a dot product, get scaled by root dk to prevent the values from blowing up. Then softmax converts the scores into probabilities. Those probabilities weight the values, and the weighted sum is the input. The paper writes this as one question: attention of QKV equals softmax of QK transpose over root dk times V. The unpacked version per position is below here. Now let me show you what this looks like with a concrete example. I've typed artificial intelligence is transforming the text into interactive transformer visualization here, built by Georgia Tech. This is a real GPT-2 model running in the browser. Each token gets projected into QKV vectors. You can see them on the left side here. This matrix in the middle is the dot product of Q times K transpose. Each cell shows how much one token's query matches another token's key. That's the QK transpose from the equation. There's a normalization or scaling step here that divides the raw score by root dk to keep them getting too large. Then softmax converts them into probabilities. Each row sums to 1. Without that scaling step, the dot products would grow with the dimension. Softmax will saturate, and it just wouldn't train. Now, the model multiplies these attention weights by the value vectors and sums them up. That weighted sum is the new representation for each token. That's the full equation in action. Notice here, it says head 1 of 12, and let me switch to another head. See how the pattern changes? Different heads focus on different relationships. That's why we need multi-head attention, which we will get to next. One way to think about the whole process, it's like a search engine. Your query is the search terms that you typed in. The keys are the indexed metadata on every page. The values are the actual page content. The engine scores your query against every key, ranks by relevance, and returns a weighted mix of the top content. Now, one extra detail that's easy to miss. Attention is asymmetric. Just because position A pays attention to position J, doesn't mean J pays attention back. Think about the sentence, artificial intelligence is transforming the world. The word transforming might attend strongly to intelligence to understand what's doing the transforming, but intelligence doesn't necessarily need to look at transforming the same way. This lets the model capture directional relationships. It's pretty limiting that one attention head can only learn one type of pattern. This multi-head attention diagram from the paper shows the solution. You run m independent attention operations in parallel, each with its own Q, K, and V matrices. The output gets concatenated and passed through a linear projection to get back to the original dimension. Let me show you what this looks like in the same model. Here's the full transformer block from the same GPT-2 model. You can see all 12 heads fanning out from the input. Let me click through a few. Head 1 has one pattern. Head 9 looks completely different. Each head is focusing on a different relationships in the data. After the attention layer, the outputs from all heads gets concatenated. Then there is a residual connection that adds the original input back. Next comes the multi-layer perceptron, or MLP, which is just two feed-forward layers that refine each token's representation independently. Another residual connection after that. And on the right, you can see 11 more identical transformer blocks. Stacks all of them, and you have GPT-2. One more thing, attention treats its input as a set, so it has no built-in sense of order. The model adds positional encoding to the input embeddings. Without those, the transformer wouldn't know whether a token was first or last in the sequence. You stack a bunch of these blocks, and each layer builds a more abstract representation on top of the previous one. For a few years after 2017, transformers dominated language, while computer vision kept running on CNNs. Then in 2020, Dostoevsky and colleagues at Google trained something straightforward. Just treat an image like a sequence and feed it into a transformer. That's the vision transformer, or VIT. You take an image, chop it into a grid of patches, the 16 by 16 pixel each, and flatten each patch into a vector. Then each vector becomes a token, exactly like a word in NLP. You add additional embeddings so the model knows where each patch sits. Attach a classification token at the front, and run the whole thing through a standard transformer encoder. Same query, key, value, mechanism. On ImageNet, VIT matched or beat the best CNNs when you gave it enough training data. That was a turning point. It proved that attention works for images as well. Since then, transformers have spread across vision. DETR brought them into object detection. Segment anything scaled that idea up to segment everything in an image. The architecture that started in NLP turned out to be general purpose. And one of the nice things about attention in vision is that you can actually see what the model is doing. If you visualize the attention weights for a given patch, you get a heat map of which other patches it's looking at. Some heads focuses on edges and textures, like early CNN layers. Some pick up object boundaries, separating foreground from background. Others capture long-range spatial relationships. The Dino paper trained VITs with self-supervision, no labels at all, and the attention maps still cleanly segment objects. The model learned where the boundaries are just from figuring out which patches should attend to each other. That kind of transparency is hard to get from a CNN. To wrap up, attention lets every position in a sequence decide which other positions matter most. Core mechanism is query, key, and value projections combined through a scale dot product. Multi-head attention captures multiple types of relationships at once. And Vision Transformer proves that the same idea works on images. You just treat patches as tokens. Today, Transformers sits behind nearly every state-of-the-art systems in both language and vision. I will end with this funny meme image from Andrew Karpathy. Attention is all you need, whether your data is words or pixels. Thanks for watching.